Good afternoon, PAD and POS 316ers. This is our short mini lecture reviewing t-tests, where we're evaluating the means of two random samples from two populations. And we discussed this in class this past week. T-tests are hypothesis testing about the means of two simple random samples that are taken from two populations. So the way to think about this is if you have two populations, you might be talking about a population of cats or a population of dogs or a population of students from UAlbany or a population of students from St. Rose. So you're looking to examine the similarities or differences in the means between these two populations based on two random samples, one taken from each of the populations. Now we use t-tests when the sample size is small. The rule of thumb is when it's below 30, or when we are comparing before and after, which I've also referred to as pre and post scores for matched variables. When we have more than 30 observations and we're not doing a pre-post, you can use the z-statistic to compare the means of two random samples. We use the t-distribution to perform our t-tests. The t-distribution is similar to the normal. It approximates the normal as we add more observations, which is why we can use the z-statistic when we have more than 30 observations. So this specifically means that we're using the t-statistic and we're using the t-distribution in order to test our hypotheses. So a t-statistic is similar to a z-score. It tells us the distance away that the observation is from the mean. Except that instead of the normal distribution, we're using a t-distribution. And we use a t-distribution because when we have smaller numbers of observations below 30, our distribution looks different than the normal. So we can't use the normal in that circumstance. Also, when we're looking at before and after pre-post data, we're actually using the differences between the pre and the post in order to test our hypothesis, and that distribution looks different. So if we're actually thinking about what is the visual distinction between a standard normal distribution or a normal distribution and our t-distribution, you can see that the t-distribution is more squashed. We can see that we have fatter tails and that we have less observations that are concentrated in the center. So this shape really is indicating some uncertainty about the t-statistic. We'll call it a sloppier version of the normal distribution. We don't have as much data, which would provide us with a nicer and more precise shape. So with the normal, we can very clearly see where we might have outliers or observations that are further away from the mean, right? Because these tails are slimmer. So the number of observations out here is fewer, whereas with the t-distribution, there are more observations that are concentrated as far away as 2 or 3 standard deviations from the mean. So as I said before, this is our t-distribution right here when we have observations smaller than 30. When we have observations more than 30, our t-distribution starts to look more like our z-distribution, which is also just the standard normal. So we use the t-distribution to test hypotheses, specifically the means of hypotheses that are about the means of two random samples. So this is for questions like, are dogs and cats, do they have equal intelligence? Do UAlbany and St. Rose students drink the same amount? Do voters in Georgia and New York State have the same income? So we're looking at specific hypotheses that are evaluating the means of two smaller random samples. Or we can use it to compare the before and after scores for matched pairs. So we're going to first focus on an example where we're looking at the means of two smaller random samples. And what we're going to do is to walk through a process where we make a hypothesis, we gather our data, we're going to calculate the mean for each group, we're going to calculate the variance for each group, we're going to divide the variance by the number of observations for each variable and calculate our t-values, and then we're going to compare our t-values to the critical value of t that we find in our table. So step one is to make a hypothesis, and with our t-tests, we can have one-tailed or two-tailed tests. And you'll remember from hypothesis testing with p-values that a one-tailed test just means that your alternate hypothesis is either that one mean is higher than the other, or a separate alternate hypothesis would be that one mean is lower than the other. A two-tailed alternate hypothesis means that you're not specifying whether the mean is higher or lower. You're saying it could either be higher or lower. We just know that they're not equal. So we've gone through these slides where we're talking about how we could set this up mathematically. Our null hypothesis is the same for one-sided or two-sided, and that's just that the means are equal. And then for our one-sided test, we would specify either that one is larger or one is smaller, and then the two-sided test is just that one mean is not equal to the other mean. So as a review, our null hypothesis for the example we're going to work through is that our mean from one population, a sample from one population, is equal to the mean of a sample from our second population. So we're saying that UAlbany students on average drink the same number of drinks per week as St. Rose students. Our alternate hypothesis is going to be that mean 1 does not equal mean 2. So this is that UAlbany students, they just don't drink the same, or saying drink more or less, but we'll say they don't drink the same on average as St. Rose students. So remembering, let's say that this is our t-distribution. We're trying to see where that value, that difference between the means is. And we're actually looking to see if it's in this area under the curve. And if it's in this area, we're going to fail to reject our null hypothesis because it's in line with our expectations. But if it's in these yellow shaded regions, we get to reject our null hypothesis. So we could have an alternate hypothesis that UAlbany students drink more than St. Rose students, which would be a one-tailed right alternate hypothesis instead of the two-tailed approach that we're taking. And that would mean that our rejection region would be over here to the right, that we're looking specifically for an effect that says UAlbany students are drinking more. Or we could have an alternate hypothesis that UAlbany students drink fewer drinks than St. Rose students, which would be off to the left, which means we're trying to detect an effect over here that UAlbany students are drinking less. Now, as you remember from our previous video lecture, the trade-off of being specific in your hypothesis testing is that if you're pretty sure that UAlbany students, if they don't drink the same as St. Rose students would drink more, you would have a better chance of finding that effect with this one-tailed. But if in fact UAlbany students are drinking less and you've chosen a one-tailed right, you actually would not be able to tell because you'd be over here in this region, right? And if your observation was over here in this region, you would fail to reject because this is not in your rejection region. And the converse is true is if you have every reason to believe that if St. Rose and UAlbany students are not drinking the same, that UAlbany students would in fact be drinking less, and you were looking over here with your alternate hypothesis. If UAlbany students were actually drinking more, you wouldn't detect that with a one-tailed left hypothesis because your rejection region is over here, and this region over here with drinking more is not included in that specific hypothesis. So that's our first step in terms of thinking about our hypothesis and how we're setting it up. The second step is to gather your data, and if you double-click on the embedded sheet, you'll see that we have 2 rows of data, one for UAlbany and one for St. Rose. You'll see that we have 13 observations in each, which means that we have a total of 26 observations because we are talking about 26 different students that we've grouped into 2 categories, being UAlbany and St. Rose. So the next thing, oops, excuse me. Sorry about that, guys. Okay, so the next thing that we're going to do is to calculate the mean for each group. And if you double click here, you can see that I've already done that using our average function, right? So all I did was I went in and I typed in, okay, let's find the mean that UAlbany students drink, and then let's find the mean that St. Rose students drink, just using this function that you're all familiar with, the equals average. Now, after you've calculated the mean for each group, you're going to calculate the variance for each group. And you're going to do that using the var.s command because we're working with a sample. So you just go through and you would type in the var.s and you would select your data for UAlbany, and then you would do var.s and you would use the data for St. Rose. So we have two different means and we have two different variances. Your next step is going to be to divide the variance for each group. To divide the variance for each group by the number of observations for each variable. Now, the reason that we're dividing it by the number of observations for each variable instead of our degrees of freedom here, which, let me fix this, is what it says in our sheet, is because by using the var.s function in Excel, you're actually already incorporating the degrees of freedom in this calculation. So for dividing the variance, all you need to do is to divide it by your number of observations for each category. So for UAlbany, it would be take this variance up here and divide it by 13. And then for St. Rose, it would be to take the variance up here, the 6.42, and divide that by 13. Okay? Now, we're going to talk about our formula for t-values here. And what this says is just that your t-value is going to be equal to, in the numerator, you have the mean of your first variable minus the mean of your second variable, and you divide that by the square root of the variance divided by the number of observations. The variance divided by the number of observations. So that's what we have here. And this formula down here is just reminding you of what the formula for the variance is, which is just the squared deviations of each observation over the degrees of freedom. And this is what you calculated using the var.s command in Excel. So you already have this information. You already have the variance divided by the number of observations. So all we have to do is to plug this in to a formula in our sheet. So what we're going to do is to go right into this embedded Excel sheet, and you can either be following along or you can be checking on the sheet that's posted in Blackboard. And to calculate our t-statistic, we just go in here and we say, okay, it is equal to the mean, so from UAlbany minus the mean of St. Rose, and we're going to put that in parens. And then we're going to divide that by the square root of this number, right? This is the variance divided by the number of observations plus the variance divided by the number of observations for St. Rose. Okay, and that's going to give us our t-statistic. So that's right here. Now, the next thing that you're going to do is to go and use the t-table. And the t-table is linked to the PowerPoint slide that we're talking about. And you'll see that in order to find the area under the curve, or the probability, the critical value of t, you need to know the degrees of freedom. Now, we've told you that the degrees of freedom is a way of adjusting our number of observations when we're working with statistics. And when we're looking at comparing two means, right, that means that we lose 2 degrees of, or that we're using 2 degrees of freedom. So 1, 2, 1 for each sample that we're looking at. And then we take a 3rd degree of freedom because we're looking at less than 30 observations. So we had 26 total observations, and then we subtract 3, and we have 23 degrees of freedom left. So we have our 23 down here, and then we know that we're doing a two-tailed hypothesis test, and our alpha value I told you is 0.05. So that means that our critical value of t that we're getting from this table is 2.069. Okay, so just remember 2.069. And those steps are used right here to tell you how to use the table. We found our critical value. Your next step is to compare the critical value, that 2.069 that we found in the table, to your t value. And our t value, if you'll remember, was 0.12008. So if your t value is higher than the critical value, you reject. But since 0.12 is lower than 2.069, what we're going to do is fail to reject our null hypothesis. We're saying that there's not enough evidence to tell us that our means are statistically different. So the final comparison is here with that explanation of our t-statistic is lower, so we're failing to reject, which just means that there's not enough evidence that St. Rose students are drinking more or less as compared to UAlbany students. Now, in Excel, we went through this process where if you have your data right here that we were looking at, you can use a shortcut where you're actually, if you click on File, and you click on Options, you can go to Add-ins, and your add-ins will give you the option to say, please put in the analysis tool pack, which is what we're going to be using for this shortcut. And once you put that analysis tool pack in, you would go to Data, the Data tab right up here, and you would go to Data Analysis. And for this example, what you would do is you'd look at all the options that are here, and you would select the t-test to sample assuming unequal variance. So we're going to click on that, and that will tell you to select your variable 1 range, where you're selecting all of the numbers for UAlbany, the variable 2 range, where you're selecting all of the numbers for St. Rose, the hypothesized difference in your null hypothesis, which is 0, your alpha level, which is okay. And with all of that, you just click OK. And it's going to give you this output. And I'm going to move this to over here so that we can compare our output to what we calculated. So we can actually see that the means that Excel calculates are the same. The variance is the same. Our number of observations is the same for each variable. You'll notice that they divided up by variable 1 and variable 2. The hypothesized mean is 0. Our degrees of freedom is 23, so we've gone over that. We get the t-stat of 0.12008, which matches what we calculated by hand. And then remember that we're doing a two-tailed test. So our critical value of t is 2.068, which is we also we calculated that, it rounded up to 2.069. And based on that, we would fail to reject. You could also do this using the p-value that's calculated in here for the two-tailed test. And remember that our alpha level is 0.05. So if, in this case, our p-value is higher than our alpha value, we would also fail to reject. So everything is fairly consistent here. So this is the end of our mini lecture on doing t-tests with small numbers of observations, comparing the means of two small observation samples. The next mini lecture will be on doing the pre-post with t-tests. So enjoy!